All right, exponential growth, the more you have, the more you get, okay? For exponential decay, the less you have, the less you lose. Quantities that grow or decay by a factor or a percentage at regular intervals are called exponential, okay? So things that exponentially grow really fast. Things that exponentially die or decay really fast, just depending on what their rate of change is. Okay? So they're different than linear. So the rate of change of a quantity is directly proportional. So that's how you know. Today you're going to know this is all exponential growth and decay because these are the exponential and decay notes. But when you're doing problems on a test, on a practice test, and everything's kind of mixed up, not done in order, how do you know when you have to do exponential growth? This right here. You will see this, some wording of that in the question. It'll say, rate of change of quantity is directly proportional to. Something along those lines. That's the key words you're looking for. When you see those words, you know it's exponential growth or decay. Exponential growth or decay. Okay? It's the only thing it is. So mathematically, we're talking about a rate of change, right? The rate of change of y. Another way of saying the rate of change of y is dy dx, right? Rate of change. Rate of change is derivative. That's what derivative is. Of y is dy dx, right? With derivative of y with respect to x is directly proportional. There's a value that we're gonna talk about today. It's k. It's not a variable. It's what we call a constant of proportionality. It's a value that we have to figure out, but it's not a variable. Okay? And then to y. So when we say the rate of change of something, of a quantity, y, is directly proportional to y, what we're saying is this guy right here. We're going to be using this guy on every single problem we do today. Okay, every single problem we do in here, we're going to be using that because of this statement here. You will see this statement or something like this statement in every single problem we do. That's how we know it's direct. It's exponential growth and decay. All right. Okay, so first thing I want you to do. This one's review, but it's going to be important for what we do later. So what I want you to do is solve this guy like you have been doing. Solve it like you have been doing. Separate and solve, just like you've been doing. Okay? Okay? So t is the independent, y is the dependent. So we're going to get t's on one side. Y's on the other. Just like we've been doing. So we get 1y dy equals k dt. Okay? And then we integrate both sides like we've been doing. One over y. What is the antiderivative of 1 over y? Natural log of y. Good. Natural log of y equals, you can put bars around it if you want, just to make sure that's always positive, right? K is not a variable. So it's not going to be k squared, 1/2 k squared. K is just a number. K is a value, okay? So k is going to get a t. Okay? It's a constant of proportionality that we use when we're doing these types of problems. Okay? Then we stop there. Well, we don't have any values to plug in like we used to, right? So the only thing we have to do, if we have no values to plug in, we solve for y. So how am I going to solve this guy for y? What do I need to do to solve this guy for y? Mm-hmm.
Set E as the base, so to speak.
Mm-hmm. Oops. KT plus C. E to this power equals this guy right here. E to the KT plus C equals y. All right, I'm going to move this guy up here. Okay. K we know is a value. T is a variable. What is C? What is C?
Constant.
A constant, right? So I'm going to break this up even further. If I want to separate these guys here, right? This is the variable part. This is the constant. How can I do that?
You split it into A to the KT times E to the C. E to the C is a constant, so I think you can change that to a C and multiply that to.
Yeah, exactly. So I can do that. That's by the basic exponent rules, right? Basic exponent rules say if you have the same base, you add their exponents, just like this. So if I want to break that up, I can break that up. Okay, the reason I did that is because, let me highlight, this guy right here is a constant. That guy is a constant, okay? So in other words, so I'm going to rewrite it. Instead of saying this guy like that, what I'm going to say is I'm going to call this guy capital C. I'm going to call this guy capital C. What capital C is the initial amount. Initial amount. Okay? This is the guy we're going to be using the entire day. The entire set of notes, we're going to be using this guy on every single one of our problems. It's going to save us some time, actually. Okay? That's the guy we're going to be using. Because every single problem, we're going to have to be separating and solving. Solving by separation. Okay? Okay, so keep that guy handy. So let's look at the first actual problem. Let's look at the first problem. Read the problem. Underline the part where it tells you this is an exponential problem. How do I know this is an exponential growth problem?
It says assuming the rate of increase of the population is directly proportional.
Yep, right there. Yep, that second sentence, right there. Right, rate of increase is directly proportional to the population. Right there tells us this is going to be exponential growth. Right now, it's kind of obvious, but in April, when we're reviewing for the test and we're doing a practice test, and you have a problem, and you're like, I don't know how to do this problem. I'm going to bring back to it, and I'm going to underline that, and I'm going to be like, remember when we see these little phrases? That means exponential growth. Okay. Okay. So the first part says bacteria in a culture. So a lot of these problems are bacteria related. A lot of them are disease related, population related, anything that grows exponentially. Things that grow exponentially that we see are usually bacteria, population, disease, things like that. Okay, so a lot of them are going to be that type of problem. Okay, so bacteria in a culture increase from 400 to 1600 in 3 hours. Assuming that the rate of increase of the population is directly proportional to the population, find the appropriate equation. Okay, so the equation. All right, so the first thing I want to do is write my equation. Which equation are they talking about? The same one I told you we'd use in every single problem, right there. Except I'm not going to use y's and x's. I'm going to use things that are specific to this problem. So in this question here, what is my independent variable going to be? What is the independent? What are the two variables? What are the two variables in the bacteria problem? Time, right? And population. Time, it's growing over time. Time, more 99% of the time, if there is time involved, it's going to be the independent because we can't control time. Population, is the dependent. So I'm going to rewrite it. D, instead of Y, I'm going to write capital P for population because that's the dependent. And then we said time is the independent. Well, instead of Y, I'm writing P for population, right? Solve that guy. Solve that guy just like you did before. Solve it. So instead of Y on top and Y on the side, you have P. Independent is P. Sorry, the independent is T. The dependent is P. This process should look, as we do this should look very familiar to you. Okay? What do you think we're going to do now? Mm-hmm. Okay, so do that. What do we get? The natural log of P equals KT plus C, right? Solve for P. What's P going to equal? It's going to be,
Capital C.
well, before we get there, it's going to be E to the KT plus C. All right? And then we can rewrite that as right? It's the same thing. The only difference is instead of Y's, I wrote P's. Okay? How many variables do I have here? How many variables do I have in my, how many things that I don't know that I would need to know do I have in my equation? Is P a variable? Yeah, right? Plug in, right? I don't know that. I need to know that. I don't know that. This is my independent. This is my dependent, right? Those guys can stay that way. Those guys can stay that way, right? Because they're the X and the Y. But besides those, there's two things I don't know that I need to know. This guy here and this guy here. E is just a value. We know what E is. So I have to find what those two guys are. I have to figure out what those two guys are before I'm done with my equation, right? Because if I plug in, because what they're going to say is, on the next question, they're going to say, okay, plug in 6 for T and give me P. I'm not going to be able to do that because I need to find what C is and I need to find what K is. So that's what I got to do first. So to solve it, I have to figure out everything except for C and K. So what am I going to do? I'm going to use the values they've given me. They've given me a couple values, right? So let me draw a table here. So if I'm drawing an X and a Y table, what letter do I use for X? T, right? And what letter do I use for Y? Capital P. Okay. So what do I know? What do I know based on the data? What values do I know? What points? What do I know based on the directions?
Intervals 3 hours long.
Say it again.
3 hours long.
Okay, something about 3 hours long. What about 3 hours long?
The increase in the bacteria population from 400 to 1600.
Okay, so at 3 hours, what's the population? Okay. What else do I know? At 0, it was 400, right? So what I'm going to do is I'm going to plug in those two things to figure out C and K, right? I'm going to use those things. So the first thing I'm going to plug in is 0, 400. 0, 400. Where do I plug in 0 for?
0 for T.
For where is it going to be plugged into?
For T.
Okay, and where's 400 going to be plugged in?
For P.
All right, so plug them in. Okay. What do I get?
400 equals C.
The 400 equals C. Yeah, why is it 400 equals C? Uh-huh.
E to the 0 is equal to 1, so C times 1 is
Yep.
0.
E to the, this is pretty much E to the 0 power. E to the 0 power is just 1. Okay. Found out part of it. Let's go down here. So C is 400. Okay. Thank you. All right. Now I'm going to use the other point to find K. So use the other point to find K. So now I know P equals 400 E to the KT, right? I'm going to plug in 3 for T. And I'm going to plug in 1600 for P. I need to find out what K is. I need to find out what K is. So solve for K. So what's the first thing I'm going to do if I need to solve for K? Divide by 400. Yep. Divide by 400. Okay, so I get 4. K's up in the sky. I can't solve for it unless I bring it down. The only way to bring something down is by using a log. And in this case, it's going to be natural log, right? So to do that, what I got to do is take log of both sides. Okay. When you do that, essentially what you're going to do is it's going to look like this. This is the base equal to this. a second. Let me rewrite this. We need to convert it from a exponent to a base of equal. Base of equal. That's something you did in Math 3, which we're going to be needing a lot this chapter. Okay, so if you're having issues converting from exponential to log and log to exponential, look that up because that's something that is going to be super important. So log base of e of 4 equals 3k. In other words, natural log of 4 equals 3k. Solve for k. K equals 1/3 times the natural log of 4. So P equals 400 times E to the 1/3 times natural log of 4 T power. That's my equation right there. Okay, that's my equation. So now the only two variables I have are P and T. So if I plug in something for T, I get P. That's what I want. There's nothing else left in there. So now question B makes it a lot easier. Find the number of bacteria at the end of 6 hours. Okay. This one says you can use your calculator. So we're going to solve for P. Any calculator will do this. Any calculator, I mean, a TI 30, $10 TI 30 will do this. So you don't need a special calculator. You just need a scientific calculator. If you turn your phone over to the side, it turns into a scientific calculator. Okay. So I got to figure out, first thing I'm going to do is the powers. And then I'm going to take e to that power. Okay, so 1/3 ln of 4. So natural log of 4 divided by 3. And then times 6. That's the power. I'm going to take e to that power. And then I'm going to multiply it by, 400. $6,400. Okay. Now, when you're doing these problems, you should always do the common sense check. Common sense check means I have a table up here. If I was to plug in a 6, would that number make sense? Would that number fit the pattern? If it does, then you go with it. If it doesn't, if you get a negative number, or you get a number that's super high, or you get a number that's lower than 1,600, you know you did something wrong. Okay, you know you did something wrong. Okay? Always double check your answers to make sure it makes sense in terms of the problem. Okay? All right. Okay, so let's look at radium. Radium-226. Radium-226 loses its mass. So this one's decaying. Not growing, it's decaying. It loses its mass at a rate that is, here we go, directly proportional to its mass. Right there. That tells us it's going to be an exponential decay or growth. If its half-life is 1,590 years, and if we start with a sample of radium-226 with a mass of 100, find the formula, find the equation. So what I want you to do is find the equation. Find the equation. Which equation am I talking about? This equation here. Don't use x's and y's. What is x? What is y? It makes it easier if you know what x is and what y is. So start right there. D something over D something equals K times something. And then solve that like we've done. And you're going to get something that you recognize. Instead of x, what do we write?
M for mass or
No. Time. Years. Time. Okay. What do we write for the dependent? Y. M. R for radium. Doesn't matter what you want to use. In my notes, I used R for radium. You can use M for mass. That part is up to you. Okay. So you solved it, right? But then you got this. Right? How did I do that so fast? Without even looking at my notes. It's the same every time. So this step right here is not needed. It's not needed. Now, if you want to do it, you can. I'm not saying don't do it, but it's not needed because you're always going to end up with the same thing, right? You're always going to end up with y here and x here. Y equals CE to the kx. And then we change x to t, and we changed r to y. Okay, so that saves you some time on these. That'll save you a lot of time on these. Okay, but again, if that doesn't make sense, do it the long way. Okay, I can't tell you how many people don't understand this. They're like, they don't see the shortcut. That's fine. Shortcuts are only good if you understand them. If you're just using shortcuts to use them, you're gonna dig yourself a hole that you can't get out of because it's not gonna make any sense. When you see this problem on a test, you're just gonna, So if what I just said does not make any sense at all, solve it. Put the T's to the right, put the R's to the left, and solve it the way we've done for the last 2 or 3 problems. Okay? Don't do this. Okay? But I'm just showing you there's a pattern. It's always going to be the same thing. It's always going to be the same thing. Okay? Okay, so R and T, or T and R, are independent and dependent. Those guys are going to stay, but we still don't know what C is, and we still don't know what K is. We need to figure out what C and K are to find the formula, to find the equation. Okay? So what's the first thing we can do to find? What's the first thing we can do? Use the table, use the information we have. Yeah. So what information do we have? Sorry, what? Mass and time, right? What do we know? At 0, it's 100 milligrams. I have 100 milligrams of radium at the start, right? Mm-hmm.
By 1,590 years, it may be 0.
So at time 0, it's equal to 100, right? That's what that says. We've seen that before. This guy right here is equal to 1 whole. So that means 100 equals C. Okay, so we got R equals C. Oops, not C. 100 E to the KT power. So I got C, but I got to figure out K now. What other piece of information do I have? Mm-hmm.
1,590 years, since its half-life is 1,590 years.
Okay, so what does that mean? What is a half-life? What is a half-life? You learn it in chemistry. What is half-life? What is half-life? Well, what is half? What does half mean?
It loses half of its mass every 1,590
It loses half of its life, right? Every 1,590 years. So every 1,590 years, half of its existence is still there. All right, so let me make a table. I didn't make a table to begin with. I should have made a table. So we already did 0, 100. So how would I write that other value?
1590 and then 50
1590 for which one?
on time.
For time. And then what'd you say? Say it again. 50 for radium. Good. That's what half-life means, man, right? And then in another 1,590 years, it would be 25. And in another 1,590 years, it would be 12.5. That's what half-lives are. So it never goes away. This radium will never go away. If you keep taking half, keep taking half, keep taking half, that's the idea of half-life. It always is going to exist. Okay? Okay, so let's plug in T and let's plug in R and let's see what we get for K. Oops, nope. Okay. Solve for K. Divide by 100. Divide by 100. You get 1/2 equals E to the 1,590K. Again, K, my variable's up in the sky. I got to bring it down. The only way I can solve for it is by bringing it down to Earth. To do that, I have to change it. The only way to bring something down is by taking a log. In this case, a natural log, since it's got a base of E. So it's going to be Natural log of 1/2 equals 1,000. Natural log of 1/2 equals 1,590K. That's why we have logs. If we're trying to solve equations where the variable's an exponent, that's why we use logs. Any variable that's up in the sky that we need to bring down to Earth to solve for it, we use logs. That's why we use logs so often. Divide by 1,590. K equals 1 over 1,590 times the natural log of 1/2, or 0.5. So I'm going to plug that in for K. So R equals 100 E That's the formula I'm going to use. Okay, so use that formula for part B. Do part B now. Now we have the formula, hard part's done. Hard part is done. So my answer, I get 64.6655. Okay. I go back to my table to see if that makes sense. So if I was to put 1,000 in here for years, would 64.6655 be reasonable? Yeah. It's right in between, right? It's right in between these amount of years. Okay. When will the mass be reduced to 30 milligrams? 30 milligrams. Okay, so we're going to use our equation. $30 milligrams now. Where do I plug in 30? Per T?
Or F, or for the dependent. Sorry.
Which is R or M, whatever you guys chose. Yep. Times T. How do I solve for t? Anybody? Yeah.
Divide by 100 first.
First thing, divide by 100. I get 3/10. Okay. How do I solve for t? You've done this before.
There are a few ways that we can go about this, but one way I'd say take the natural log of both sides right now.
Change it to a log. So let's see. So if I change it to a log, it's going to be this guy, this base equal, or of that equals that. So natural log of 3/10 equals this guy. Times t. Well, it's this guy times t. So it's a bunch of multiplication. So just divide by what you don't want. Don't round until the very end. Notice I have not rounded. There's no decimals anywhere in my equation. You don't see any decimals because once you do a decimal, you're rounding. And then if you round again and then you round again, your answer is going to be far off. That's how, and on a multiple choice question, which you're going to see these on, you're not going to be able to match. Leave the decimals for the very end when you're solving for t. So the only thing left here is t. Now you can do all that stuff in your calculator and you can find, let's see, clear up. So top will just be natural log of 3/10, or you can actually put everything in there. Let's see if I can do this correctly. Natural log 3 divided by 10. Okay, that goes on top. And then on bottom, it's 1 over times parentheses natural log of 1/2. Okay. So I get 2,761. Point. Always go at least 3 decimals. 775 years. Go back to your table. Does that number make sense? If I put 30 in and around 2,700, is that going to make sense? So if I put 30, let me say, 30 mgs, is 2,761.775 going to make sense? Yeah, it's reasonable. It is reasonable. Okay. All right. So what I want you to do now is do number 4. It's population now. Nothing's changed. Nothing has changed. Still time. This time instead of radium, it's population. Okay. You still see proportional to the population rate of change. Okay. Probably won't finish this today, but at least give it a shot and see what you get. So when I create, I'm not, but just a question before, as you're working. As I create my table, they give me years, 1930, 1960, 1990, right? That for time. What would probably be a better way of doing time as opposed to that? Could I plug in? Because I'm going to have to plug in 1,930. That's a big number to plug in.
Instead of 1930, you can put 0, 1960, 30, and then 1990, 60.
Yeah, that's probably what I would do. Now, is it wrong if you do it the other way? No, it's just but your calculations are going to be very big for no reason. I'd rather plug in 0, 30, and 60 than 1,930, 1,600, or 960, 1,990. So yeah, that would probably be easier to use for that.